Hi, Year 14. Today we are going to turn to page 9 in our notes and we are going to consider the spin-spin splitting patterns that we see in high-resolution NMR spectra. Now, if we recap what we have already said about NMR. So first of all, when we are analysing a spectrum, we look at the number of peaks. And I'm hoping that you remember that the number of peaks tells us about the different types of equivalent hydrogen groups. Then the position of the peak tells us about the chemical environment of the hydrogens. The area under the peak tells us how many hydrogens we have. And then we touched on it last lesson really briefly. The peak splitting pattern tells us the number of hydrogens on adjacent carbons. Now we're going to focus on this peak splitting pattern this lesson. But before we go any further, we are going to really understand and state the rule for this peak splitting. So we've said before that it shows us the number of hydrogens on the adjacent carbon, and the rule is there for you. The rule is that the number of lines in the splitting is 1 plus the number of hydrogens on the adjacent carbon. Now this will be a bit more clear when we look at a couple of examples. So if we have a singlet, so if the peak hasn't been split, if it's only one line, that means that there are no hydrogens on the neighbouring carbon. If we have a doublet, according to the 1 plus rule, that means that there is one hydrogen on the neighbouring carbon. If we have a triplet, according to this 1 plus rule, that means that we have a triplet, which is 3 lines. So that's 1 plus 2 hydrogens on the neighbouring carbon. If it's a quartet, according to this 1 plus rule, that means that there are 3 hydrogens on the neighbouring carbon. Now, if we have more than 4, there are exact names for it. We can just call it a multiplet, but it's not on our spec, so we don't really need to be that concerned with it. Now, if we take a couple of spectra and we look at them so that you can see exactly what I mean by this 1 plus rule. Now, if we look at the first spectrum here and we look at ethanol. Now, you can see we've got the high resolution spectrum there. And if we deal first of all with the integration that we covered in a previous lesson. Now, there are the integration numbers that I'm circling just now. 0.2, 0.4, 0.6. I want to get this to the simplest whole number ratio by dividing across by 0.2. So this will simplify to 1, to 2, to 3. So this tells me that this peak is caused by 1 hydrogen, this quartet is caused by 2 hydrogens, and this triplet is caused by 3 hydrogens. Now I know a bit about the chemical shift, we covered it in last lesson. We've got this electronegative oxygen, which causes the nucleus of the protons to be deshielded, and it will shift the peak downstream. So I know that this peak at just over 5 parts per million is caused by this hydrogen here. I know then that the peak between 3 and 4 parts per million is caused by these 2 hydrogens that I'm underlining in red. Then I know the peak, the triplet, that has the least chemical shift at around 1 parts per million. It's furthest away from this electronegative oxygen, so it's furthest away from its deshielding effects. That peak is caused by these 3 hydrogens, and that fits in with our integration numbers that we worked out just a minute ago. Now we want to concentrate on this splitting pattern. So let's take this blue hydrogen here and let's look at it. So we can see clearly that it is a singlet, S for singlet. Now we can see that it's not joined to a carbon, it doesn't have any adjacent carbon, so there are no hydrogens on the adjacent carbon, and according to our 1 plus rule, that means therefore that it is a singlet and its neighbour is just an oxygen. There are no neighbouring hydrogens. Now if we take our 2 red hydrogens, okay, and we can see that it's this peak that we're considering. Now this peak is a quartet, Q for quartet. Now I'm looking at the carbon adjacent to it. So I can see that on the adjacent carbon there are 3 green hydrogens. Now it splits according to the +1 rule, so 3 + 1 is 4. That means that this peak splits into 4 and it is a quartet. So therefore when I want to fill in the neighbours are these 3 green hydrogens. Now if we go to the last peak, let's go to this peak at 1 part per million. We can see that this peak has been split into a triplet, T for triplet. Now if I look to see what's beside it, well, it's the red hydrogens that are beside it. There are 2 of them, so according to the 1+ rule, 2 + 1 is 3. That explains why it is split into a triplet. And I can say that the neighbours there, if I keep the colour coding correct, the neighbours there then are these red hydrogens. Oh, apologies. So these red hydrogens. Okay, so I can get lots of information, as you can see. Now if we go and we consider another example, let's consider the example of propanoic acid. Now I can see in propanoic acid that there are 3 groups of hydrogens and I have got three peaks. Now the integration trace has been left off, but I can see that the integration there would be 1 to 2 to 3. So one of the peaks is caused by 1, another peak is caused by 2, and another peak is caused by 3. Now the peak with the greatest chemical shift will be caused by the hydrogen that is right beside this electronegative oxygen. So this peak is caused by this hydrogen. Then the CH2s, well, they are the ones that are next closest to this electronegative oxygen in this carbonyl group, which is also de-shielding. So these 2 hydrogens here are causing this peak. The peak then with the least chemical shift will be caused by these 3 hydrogens. Now we want to look at the splitting pattern. So this one is a singlet, you can see. Oh, we've got our singlet there. We'll keep it in red. Now this singlet doesn't have any hydrogens on an adjacent carbon. In fact, it doesn't have an adjacent carbon, so its neighbour is just the O. Then we have got this blue peak. You can see clearly as a quartet, and I can see that there are 3 green hydrogens on the neighbouring carbon, so its neighbour is this CH3, and it's fitting into this 1+ rule. Now the last one then, our peak is caused by these green hydrogens. We can see that it's a triplet, and according to the 1+ rule, well, there are 2 hydrogens on the adjacent carbon, so that explains the fact that it has split into a triplet, and its neighbour is this CH2. Okay, now folks, none of those examples were in your notes, but you can see there at the bottom of page 9, you've got this example of 1-bromopropane. And 1-bromopropane can be analysed in exactly the same way. We had looked at it last lesson and we had talked a bit about the integration trace, and now we should be able to explain the splitting pattern for this 1-bromopropane also. Now if you turn on to page 10 then, you can see that that's all explained for you in your notes, and you've got a reference there that you can look at, or you can go back and play my video again should you need to. Now if we look at this 1-bromopropane before we leave it, I can assign which hydrogens are causing which peak. So I can see that this peak here, we'll call it the red peak, is caused by the CH3s at the end, and it might be helpful if I drew out this 1-bromopropane. Okay, so these CH3s at the end, adjacent to the CH2, is causing this peak. And I know that because those hydrogens are furthest from the electronegative bromine. Now you can see it's split into a triplet, and if we look at the two hydrogens beside it, well, there are two, so according to the 1+ rule, it's right that it should split into a triplet. Now if I look at this, and we'll call it the blue peak. Now this is caused by these two hydrogens here. Okay, and I know that because those are the ones that are next furthest away from the de-shielding effect of this electronegative bromine. Now this is a multiplet, and I need to look. I have got 3 hydrogens to the left of it, and I've got 2 hydrogens to the right of it, so it will be split into 6 according to the 1+ rule, and if you look carefully you can see that it has been split into 6. Now our last group of hydrogens then are these 2 hydrogens. They've got the greatest chemical shift because they're right beside this electronegative bromine. There are 2 hydrogens on the carbon adjacent to it, so it's been split into a triplet like we'd expect. So the hydrogens that are causing this peak are the CH2, and we have got adjacent to it another CH2. And that fits everything that we have covered, and you've got that typed out for you on page 10. Now let's look at another couple of examples that you've got in your notes. So for question 3, we are told in the spectra below, identify the sequence in the molecule that produces the splitting patterns. Okay, and this NMR is all about getting little sections of the molecule, and then you can join it up with what you know from mass spec and what you know from IR to sometimes come up with the structure of a molecule. Now if I look carefully at 3A, I can see that I have got a quartet and I have got a triplet. Now the quartet must be caused by hydrogens that are adjacent to a CH3. The triplet must be caused by hydrogens that are adjacent to a CH2. So if I look there, I can say for sure that there must be this CH3-CH2 sequence somewhere in the molecule. Now if we go to spectrum B, we've got a quartet and we have got a doublet. Now this quartet must be adjacent to a CH3, and this doublet must be adjacent to a CH. So somewhere in the molecule I have got this sequence. Look at spectrum C. This is a triplet, this is a doublet. The triplet must be adjacent to a CH2, and the doublet must be adjacent to a CH. We've got 2 triplets, and in order to have 2 triplets, well, they both must be caused by hydrogens that are adjacent to a CH2 and a CH2. So somewhere in the molecule that caused this spectrum, we have a CH2-CH2 sequence. Patterns in the following molecules. Now, I'm looking to see what's beside it. So these 3 hydrogens are adjacent to a CH2, so they are definitely going to be split into a triplet. Then the 2 hydrogens are adjacent to a CH3, so that peak will be split by the CH3 into a quartet. The 3 hydrogens here are adjacent to 1 hydrogen, so this peak will be split into a doublet. We have got 1 hydrogen here, which is adjacent to 3, so this peak will be split into a quartet. If we look at the last molecule then, these 3 are not adjacent to any carbon with hydrogens on it, so the peak that is caused by these 3 hydrogens will not be split, it will remain as a singlet. If we look at these 2, well, they're adjacent to a carbon which is joint to 2, so this will be split into a triplet. If we look at these 2, well, they're adjacent to the carbon which is joint to 2, so this will be split into another triplet. And that's a sequence like we just studied for question 3, the spectrum D. We have a CH2, CH2, And like we had in spectrum D for question 3, we had this CH2 sequence. Predict this me on page 11. You've got a table to sum it all up. Now I'm hoping as we analyse those spectra that you noticed that a singlet, a doublet, a triplet and a quartet always appears the same. So you will be asked to sketch spectrum in exam questions, and it's really important when you're sketching a doublet that the two peaks are the same height. It's really important when you're sketching a triplet that the relative size of the peaks, like you can see, is 1 to 2 to 1. For the quartet then, it's really important when you're sketching it that it's 1 to 3 to 3 to 1. Okay, now it's useful just to sum up everything that we've talked about, like you can see on my screen, into that table then on page 11. Now one last thing I leave you, and before I get you to try some. It's very important when we are looking at molecules that we look at the whole structure of the molecule and not just the neighbouring atom. Now you've got these notes on page 12. Now if we look at example 1 so that you can see what I mean by that. Now if we look at, or if we were to consider, a spectrum for butane. In a spectrum for butane, we would see two sets of signals. We would see a triplet due to the CH3 groups, and we would see a quartet due to the two CH2 groups. Now the signal due to the hydrogens on carbon 2 is not a hextet. The two hydrogens on carbon 3 are chemically identical to those on carbon 2. So if I were to go into my molecule, it's really important that we realise that those 4 hydrogens are chemically equivalent. And chemically equivalent hydrogens do not affect this splitting pattern. So if we were to say we have got a triplet due to the two CH3 groups, there are 2 hydrogens on the adjacent carbon. So 2 plus 1 would split that into a triplet. Then we have got a quartet due to these 2 CH2 groups. There are 3 hydrogens on the adjacent carbon. So 3 plus 1 splits that into a quartet. So we're realising that these 4 hydrogens here in green are chemically equivalent, and these 3 and these 3 are also chemically equivalent. So remember that chemically identical or equivalent hydrogens do not affect the splitting pattern. Now if we were to go and we were to look then at cyclohexane. Now for cyclohexane we would get one signal, and that would be a singlet caused by these 12 hydrogens, but there are no chemically inequivalent hydrogens, so there are no hydrogens there to split this singlet. So all the hydrogens, like I've said, are chemically equivalent. There are no chemically inequivalent hydrogens on adjacent atoms. The signal will be a singlet because of this 0 plus 1 rule, making it a singlet. And that's 0 plus 1. The 0 just means that there are no chemically equivalent hydrogens on adjacent atoms. If we go then and look at the last example then, we have got ethane 1,2-diol. Now in ethane 1,2-diol, we would see 2 sets of signals. We would have a singlet due to these chemically equivalent hydrogens here. Now the ones that I am boxing as red are also chemically equivalent. So the 2 CH2 groups will be a singlet because there is only one hydrogen, because there are no hydrogens on it, there are no adjacent carbons even, so there are no hydrogens to split this singlet. Then we will have a singlet due to the OH groups because there are no hydrogens on the adjacent carbon to split this peak. So if we look at the bullet points, the signals due to hydrogens on the OH groups are always singlets. The hydrogens on the CH2 give rise to a singlet because the hydrogen atoms on the adjacent CH2 are chemically equivalent, so they don't couple, and the hydrogens on the adjacent OH groups do not couple. So just summing up for those three examples, it's really important to look at the whole molecule when you are deciding whether any of this spin-spin splitting or spin-spin coupling will happen.